The other topic for the first day of week 12 is the solution to plane waves with reflection at a material boundary with oblique incidence. So we set up last time this problem where we have a wave that's incident, we have a reflected wave, and we have a transmitted wave. And we didn't talk about the polarization of the electric or magnetic fields because the solution is different depending on whether we choose parallel polarization or perpendicular polarization. And as a reminder, parallel polarization means that the electric field vector lies in the plane of incidence. Which is the plane that contains all of the k vectors and the surface normal vector. So the plane of incidence is otherwise known as the page or the screen. Perpendicular polarization has the opposite situation. That has the electric field is perpendicular to the plane of incidence. There are other names for both of these situations. Parallel polarization has the alternate name TM for transverse magnetic, because the magnetic field is perpendicular to the surface normal vector. And the plane of incidence. Perpendicular polarization is also known as TE, or transverse electric, because the electric field is perpendicular, also known as transverse, to the plane of incidence. So those are the two types of problems that we can have. In a separate lecture, I'll go through all of the derivations for one of these problems. But for right now, what I just want to do is lay out the two solutions side by side. So here's what we do. I'll draw the two problems first. If we have parallel polarization, here's our material interface, material 1, material 2. I'm going to have that be the z-axis. My incident wave has this wave vector ki, and so far that's all I've been drawing. But I can draw the electric field now because I know that the electric field lies in the plane of incidence. So I need a vector that is perpendicular to ki and in the plane of incidence. And that leaves me two choices. They can be this blue electric field vector or this red electric field vector. Could be either one of those. Doesn't really matter which one we choose because it's the incident wave. I'm going to choose the blue one. So That is the electric field vector of the incident wave. Now, because E cross H has to be in the direction of the propagation vector, that means that the incident wave's magnetic field is into the screen. The requirement for the rest of the fields is that the electric fields should all have the same transverse component polarity, meaning that for the reflected wave, the Z component on the electric field is going to flip, but the we're going to say that this is the x-axis. The X component of the electric field is going to point in the same direction. So you can see here that the X components of those two electric fields are in the same direction. The transverse components of the electric field have to be in the same direction. That's the rule for when you're drawing this diagram. Then we define the transmitted wave. We've got a propagation vector for that. We've got an electric field that's got to be perpendicular to that propagation vector, and it has to have its transverse component in the same direction as that of the incident wave. So that means that it's got to point that way. Which means that for the reflected wave, the magnetic field is out of the screen because E cross H has to point in the direction of KR. And for the transmitted wave, the magnetic field is into the screen because E cross H has to equal KT. That's our problem definition for parallel polarization. For perpendicular polarization, the setup is pretty much the same, except this time the electric fields are perpendicular to the plane of incidence. Which means that my electric field, I'm going to define EI into the page like that. So if that's into the page and E cross H has to point in the KI direction, that means that HI is that way. And we can go through and define all of our other field components the same way. It's always good to do that right-hand rule check to make sure that your E field cross your H field points in the direction of the K vector. Then if you make sure of that, everything will have the right polarity. So this has gotten kind of busy looking. Let's scroll down. Now that we have all this stuff drawn out though, here's our perpendicular polarization. And there's our parallel polarization. The solutions for this are based on boundary conditions. Some of the boundary conditions are the same in both cases. In both cases, the tangential components of the electric field has to be equal across the boundary. And the tangential components of the magnetic fields also have to be equal across the boundary. These things are, all boundary conditions are true at all boundaries, but some of them are relevant and some of them are not. In the perpendicular polarization case, there is no normal component of the electric field. So n hat dot E equals 0, so we don't care. But in the parallel polarization case, there is a perpendicular component of the magnetic field, so we care about D2 minus D1, and that has to be, technically it's equal to the surface charge density, but since we're considering a lossless case, there isn't a surface charge density, so we get that. Similarly, parallel polarization doesn't have a normal component for the magnetic field, so we don't care about B2 minus B1. Well, on the perpendicular polarization case, we have to say that the normal components of the magnetic fields should be equal across the boundaries. Because of this difference, both in the problem definition in the pictures that we drew and in the boundary conditions that are relevant, we get slightly different answers for these two things. Both of them have a reflection coefficient, both of them have a transmission coefficient, but they're different. So, the reflection coefficient for perpendicular polarization, which is the reflected wave amplitude divided by the incident wave amplitude, is equal to eta 2 over cosine theta t minus eta 1 over cosine theta I divided by the sum of those two terms, eta 2 over cosine theta t plus eta 1 over cosine theta I. And for the parallel polarization case, we have eta 2 cosine theta t minus eta 1 cosine theta I divided by eta 2 cosine theta t plus eta 1 cosine theta I. The transmission coefficients are made up similarly. So for the parallel polarization transmission coefficient, for which we're using a lowercase tau, we have 2 eta 2 cosine theta I divided by eta 2 cosine theta t plus eta 1 cosine theta I. And then in the perpendicular case, whoops, drew that perpendicular upside down. We have 2 eta 2 over cosine theta t over eta 2 over cosine theta t plus eta 1 over cosine theta I.